Once we have identified and quantified the different sources of uncertainty, this uncertainty can be propagated to the model output. This means that we can use the model, the mathematical model, to calculate how the input of uncertainty reflects as an uncertainty on the output of the model. There are different techniques to perform these calculations. We will take a look at the classical error propagation, differential analysis, and Monte Carlo. Classical error propagation is just basic statistics, so what we have seen as properties for errors or standard deviations. This classical error propagation is only valid for linear models. The errors should be normally distributed, and ideally there is no significant covariance. So we have three very limiting assumptions. Under these assumptions, we know that if z is x plus y, then the variance of z is the variance of x plus the variance of y. So the standard deviation of z is the root of the variance of x plus the variance of y. And for multiplications and divisions, we can do the same thing. So if z is x times y or x divided by y, it can be shown that sigma z over z is equal to the root of sigma x over x squared plus sigma y over y squared. So we see that in this case we have not taken any covariance terms into account. These two cases, addition, subtraction and multiplication, division, they are very simple. But once the calculations become more complex, the calculation also becomes a lot more difficult. A second option to calculate or to do the propagation is through differential analysis. Differential analysis is also called linear uncertainty propagation. Why linear uncertainty propagation? Because it is a linear approximation to determine the uncertainty on the model output. If y is a function of x1 to xn, where x1 to xn are different sources of uncertainty, then we can calculate the variance on y using Taylor series. So we will use a Taylor series as an approximation of the function f. And in this case, this variance of y, sigma squared y at a certain time point t, is given as a sum of the variances of each of the sources of uncertainty times the sensitivity function of y with respect to xi squared. The confidence interval for the model output is then defined by the deviation delta y. This deviation will be equal to a quantile of a t distribution with a certain degrees of freedom times the calculated standard deviation. So your confidence interval will be y bar plus or minus delta y. Since our calculation uses a linear approximation through a Taylor series, this calculation that we did is only approximatively valid for nonlinear models. So for nonlinear models, this approximation is good if we are in a very small interval around the point that we are looking at, but it is not valid for larger deviations. And again, in our calculation, we did not consider any covariance between the different sources of uncertainty. However, in this case, in differential analysis, we can also include covariance terms. So we can include the covariance between the different sources of uncertainty as is given, as is shown by the formula on the slide. Take, for example, a linear model in which the total amount of nitrogen is equal to the amount of nitrogen in the ammonium plus the amount of nitrogen in a certain organic component, such as, for example, amino acids. Assume that both the components NH4 and NORG are stochastic variables, and each of them has a certain uncertainty, which we express through their variances. Furthermore, we will also assume that they are correlated, so that there is a covariance between both sources. If we then apply the formula on the previous slide to find the uncertainty on the output and total, so the total amount of nitrogen, we see that the variance for this total amount of nitrogen is the variance for the NH4 component plus the variance of the organic component plus 2 times the covariance between both terms. To obtain this formula, we have used that we have a linear model, and so each of the sensitivity functions is equal to 1. If we then also use the definition of the correlation, so the correlation is the covariance divided by the standard deviation of x and the standard deviation of y, we can rewrite this formula as the variance on NH4 plus the variance on the organic component plus 2 times the correlation between both times the standard deviation of each of the components. For our river example, we have earlier calculated the sensitivity functions of y with respect to the parameters k1 and k2, and we have also calculated the variance for k1 and the variance for k2, and this will then allow us to apply differential analysis to find a 95% confidence band. This 95% confidence band means that on average 95% of the simulated model predictions will lie between the borders as defined by this confidence band. And then if you plot it, you get this one, so you get this graph. You see that in dark blue is the mean. This is the mean of the model. And then in light blue, these are the confidence band, the upper confidence band and the lower confidence band for the dissolved oxygen over time. And then the third option for uncertainty propagation is using a Monte Carlo simulation. The advantage of this technique is that it can also be used for any nonlinear model. Due to their inherent uncertainty, we will consider that the inputs and or the parameters of the model are stochastic, so they have a certain distribution, and this stochasticity will be reflected in our Monte Carlo simulations. So again, as what we did before with Monte Carlo, we will take a number of simulations. For each of those simulations, we create a shot, a deterministic outcome of y. This gives us, let's say, n times an outcome y, and then we can use this vector of outcomes to get an idea about the mean and the variance on the outcome. The disadvantage, as always with a Monte Carlo simulation, is that you need a lot of simulations. Another disadvantage in this specific case is that it is impossible to quantify the contributions of the different sources of uncertainty. So you will just have an idea about the uncertainty, but using Monte Carlo simulation, it is impossible to determine which part of the uncertainty stems from which source of uncertainty. Of course, we will do this for different time points, so let's say p discrete time points, and this gives us then vectors y1 t1 to y1 tp up to yn t1 to yn tp. What we then do is a statistical analysis between different time series, and at a certain time point we have thus n values of the model output. This will then allow us to calculate for each of the different time points statistical quantities such as the mean, median, the variance or the percentiles. So we get a quantification of the uncertainty of the model output per time point that we have considered. So in the left plot we see n simulations of the outcome, so n lines, each of those lines corresponds to a certain outcome function y. And with this we can create confidence bands. In this case we have created an 80% confidence band for the different time points. So basically what you do is you look at a cross section, let's say the time t equal to 6. At the time t equal to 6 you look at all the different outcomes, and with these outcomes you can calculate the mean, you can calculate the median, the 10th percentile and the 90th percentile, and this will give us then the plot on the right, where you have the mean in the middle, the full line for the mean, and then a line for the 10th percentile, a line for the 90th percentile, and thus an 80% confidence band. With those simulated output values, you can also create histograms. Again, you can only create a histogram for a fixed time point. And so here, in this case, we have chosen the time point t equal to 10. And for this time point, we have created the histogram that you see on the right. So for any specific time point, we can get an idea about the distribution of the output at that given time point. Same way, we can create a cumulative distribution function at a certain time point. So this is the probability that the model output y is smaller or equal to a certain value capital Y. In this case, this cumulative distribution function will be calculated using the empirical distribution of y, which explains why the cumulative distribution function on the plot is so irregular. So there are a lot of small steps, small jumps in it, just because we use the empirical distribution function, so it's not perfectly smooth. And with the cumulative distribution function, we can also calculate the complementary cumulative distribution function, the CCDF. The CCDF is the probability that the model output y is larger than a certain value y. So we know, or from the definition, it follows that the CDF plus the CCDF is always equal to 1. So again, the CDF is the probability that y is smaller or equal than capital Y. The CCDF is the probability that it is larger than y. And so if we add those two probabilities, then basically we are considering every possible outcome for y. So the probability for this is 1. On the left, we see the CDF and the histogram as we calculated or we found on the previous slide using our simulations. And then on the right, we have the CDF and the CCDF. Both those plots are made for a time t equal to 10. And in the right plot, you clearly see that if you add for a fixed x value, if you add the CCDF and the CDF, their sum will always be equal to 1. Assume that for the river example, we did a Monte Carlo simulation for 1000 samples. The two parameters, the two inputs that are stochastic are K1 and K2, and we assumed that they have a uniform distribution. We then create those 1000 samples, so we create 1000 samples of K1 and K2 for different time points. And then with these samples, we can calculate for each of the time points the mean, the variance, and the percentiles for the output. And this allows us to create 90% confidence intervals for each of the outputs or a 90% confidence band around the output function. Then we can fix a time point. For example, in this case, we fix it at t equal to 3 minutes. And for that time point, we can create an histogram. We can calculate the CDF and the CCDF to get an idea about the distribution of the outcome at that certain time point.